Welcome. I'm glad you've joined me today to learn more about the science and engineering practice, analyzing and interpreting data. I'm Patty Works, a regional teacher partner with PIMSR, the Partnership Institute for Mathematics and Science Education Reform. This video is part of a series of modules that focus on the science and engineering practices. This video workshop can be something that's done individually or with a grade level group or PLC. You will want to have access to the following materials as we get ready to get started today. The readings that you'll need, you'll find linked in the description box below, and you'll also want a note taker, either an electronic document or paper and pen. Here's our objectives for this video workshop. During this session, we'll use a variety of resources to help you develop a deeper understanding of the science and engineering practice, analyzing and interpreting data. And we'll explore what's meant by analyzing and interpreting data for each grade band. And last, we'll help you increase your knowledge of instructional strategies that can help students develop skill in analyzing and interpreting data. Our focus questions will be, what do we mean by analyzing and interpreting data? How does student use of this practice increase in complexity throughout the grade bands? What does a lesson look like when students are engaging with analyzing and interpreting data at sophisticated levels? And what are some instructional strategies that teachers can use to help students develop an understanding of how to analyze data? So let's get started. The Kentucky Academic Standards for Science call for phenomenon-based teaching and learning, where students are actively figuring out about phenomenon. By scientific phenomenon, we mean an observable event that occurs in the universe that we can use science ideas to explain or predict. For example, students may be working to figure out how fossils of an extinct organism occur in just 2 areas on Earth, divided by an ocean, or why a particular plant is growing somewhere that it wasn't intentionally planted by humans. So how do students go about figuring out phenomena? Our standards are 3-dimensional, representing the 3 parts of the sense-making process. The science and engineering practices are what students do as they collect data and make sense of it. The cross-cutting concepts are the thinking lenses that they'll use. And the content is what students know and understand as a result of the active learning. I'll give you a moment to read this quote. Our standards call for instructional shifts. Science instruction isn't giving students laws, theories, terminology, and facts to merely memorize and recall. Instead, we want them to learn to work like scientists and engineers do. We want students to gain proficiency with using the practices as they develop conceptual understandings. As we continue to improve our own science teaching practice, improving student use of the science and engineering practices is key. This is something we want to see happening in every lesson. Please take a moment to read this quote. As noted by the National Research Council, it takes time and specific attention to fully develop student use of the practices. And that will be the focus of this video, to carefully look at the practice of analyzing and interpreting data and learn more about how to help students develop their abilities to use this practice. The 8 science and engineering practices are what students do as they make sense of phenomena. However, they aren't completely separate entities. I'm sure you'll find it's hard to use just one practice in a lesson. As an example, in a given lesson, students might be presented with an engaging phenomena, then they might ask questions about it. As they investigate those questions and plan and carry out experiments, they'll collect data that they'll need to analyze and interpret. This may lead them to making explanations or to more investigations. And all the while, they're often obtaining, evaluating, and communicating information along the way. Real science is not a linear process, but rather an interconnected web. In an effort to help teachers recognize how overlapping the practices are and how they work synergistically in classrooms, McNeil, Katzinger, and Pelletier developed a grouping of the science practices that can illustrate the nature of science shown in the diagram. We should note here that there are other groups and organizations that have grouped the practices in different ways or showed how they interact in different types of models. This is just one example. In this model, they've grouped the 8 practices into investigating practices, sense-making practices, and critiquing practices. The investigating practices focus on asking questions and conducting investigations about the natural world. The product of those investigations is data. The sense-making practices analyze the data looking for patterns and relationships in order to help develop explanations and models. A key element of science, which is often left out of K-12 instruction, is critique. The critiquing practices focus on evaluating and arguing about the different explanations and models in order to develop a stronger understanding of the natural world. The table below illustrates one way to group the 8 science practices into the investigating practices, sense-making practices, and critiquing practices. As students investigate, they ask questions, plan and carry out investigations, and use mathematical and computational thinking. As they make sense of data, they'll use the sense-making practices of developing and using models, analyzing and interpreting data, and constructing explanations. And then once those investigations have given them data and they've made sense of it, the critiquing practices of engaging in argument from evidence and obtaining, evaluating, and communicating information will come into play. As they critique their ideas, that may lead them back to collect more data, or it may lead them to new questions to investigate. In this video, we'll take a deep dive into the sense-making practice of analyzing and interpreting data. McNeil and colleagues developed a website, sciencepracticesleadership.com, which is full of a multitude of resources for teachers and administrators as they gain ability to help students use the practices. Here you see their definition of analyzing and interpreting data from the perspective of the science practices. Take a few minutes to read through this definition on the left and the bullet points in the center that help show what students do. There's also a sample performance expectation and a classroom example from the NGSS. Well, here's what stood out to me as I read that. Analyzing and interpreting data includes making sense of the data that was produced during investigations. So it's starting out with investigations, but then looking at that data. We're looking for patterns, and because they're not always obvious, we use a range of different tools such as tables, graphs, and other visualization techniques to help us make sense of the data. The bullet points in that center column that showed you what students do really focused on the fact that kids are analyzing and interpreting data to determine patterns and relationships. They're representing data in tables and graphs to help reveal those patterns and relationships. And they're considering the limitations of data analysis, such as sources of error. The example that's given And in this case, it's a kindergarten example, is of how students analyze and interpret data. There's a performance expectation that focuses on data analysis for primary students. And they use the expectation KLS1-1. Use observations to describe patterns of what plants and animals, including humans, need to survive. Well, what does that translate to in instruction? An example of a class activity helping students learn how to do this might have students doing this, using a class chart of what different animals eat and then grouping the animals in different ways based on their food sources. Students would discuss which animals would be affected if changes occurred to different food sources. So they have collected data and grouped the data so that they can find patterns and relationships. I think that example helps us see that the idea of looking at patterns and relationships in data and grouping data can be done with our very youngest learners. Analyzing and interpreting data is also a key practice in engineering. Engineers collect data during the testing of design solutions, and that data allows them to compare solutions and see how well they meet design criteria or solve the problem most efficiently within given constraints. Just like scientists, engineers use a range of tools to identify patterns in data and interpret the results. So as we get started, let's be clear on what we mean by data. Data, by definition, is information. Often we have a tendency to think of data as numeric observations, which it certainly can be. The data that scientists and engineers collect can also be written observations, photos, or drawings. Data is simply information. When we analyze, we're studying data to determine the nature of relationships of the parts and look to see if there are any patterns. When we interpret the data, we're making meaning of that data. Analyzing and interpreting data is the process of assigning meaning to information that we've collected, and then reaching conclusions about the significance, or sometimes the lack of significance, and the implications of that data. Many times, in my experience with the time constraints in the classroom, we find that we've investigated questions and collected data, but we may run short on time to analyze what that data means. And then we've really lost much of the purpose of the investigating. Students need to be aware that the data is collected for a purpose, to answer a question or evaluate a design solution. And in order to evaluate what it means, we have to have the data organized. As you and your students conclude investigation, here are a couple of guiding questions for the process. What do the data that we've collected mean? And does that data help me answer my question or evaluate my solution? And if so, how? Now that we've clarified what we mean by analyzing and interpreting data, we're going to take a look at what the standards tell us about this practice to answer the question, how does the student use of this practice increase in complexity throughout the grade bands? In the resources linked below, please find Appendix F, the Science and Engineering Practices Progression. This version is a colorful matrix from Appendix F from NSTA. NSTA provides lots of standards-based resources that are free to members and non-members alike. You'll want to open that document and scroll through to the 4th page, Analyzing and Interpreting Data. Let's take a moment to look at how this page is set up once you find it. At the top, there's some general information about the practice, and the body of the table contains 4 columns. A general description of the practice is given at each grade band, and then below that, there are bullet points giving you specific elements of the practice for that grade band. These are the behaviors that we want to see students engaging in during classroom lessons to develop their abilities with the practice at their age. At this point, I want to clarify that the elements of the practices listed in the columns underneath that grade band are not grade level specific. They are what we want students to be able to do by the end of that grade band. So by the end of second grade, fifth grade, eighth grade, and 12th grade. So if you're teaching sixth grade, which is not at the end of a grade band, you may need to scaffold that element of the practice as your students incrementally work towards that. Now, please pause the video and take a few minutes to read and highlight things that you notice about this practice. You may want to take some notes as you work. I'd suggest you might want to first read down through the grade band columns, perhaps starting with the one that you teach. What are the elements of the practice in K2, 3-5, 6-8, or 9-12? And then next, take a look at the elements of the practice and follow them across from left to right. How does this practice become more complex at higher grade levels? Take a look at the patterns that you see and think, does that raise any questions for you? What does this mean for your school and your students? Pause the video now while you work. Then you may restart when we're ready to discuss together. I want to discuss a few of my takeaways as I look at the progression of this practice. In K2, analysis takes the form of collecting, recording, and sharing observations. This is the beginning of data analysis for primary students. I noticed in the bulleted elements of the practice that there are lots of age-appropriate suggestions for how student observations may be recorded ideas, observations, drawings, and/or pictures. But looking at this third bullet in K2, even at early ages, we want students to be using those observations to describe patterns or relationships, to answer questions or solve problems. We want them to compare predictions using those prior experiences to the data that they've collected. And down near the bottom of the page, we see intended use of the practice in evaluating a design solution in an engineering task. In grades 3-5, students build on what they've done in K2, and we see a decidedly more quantitative focus on collecting data and doing multiple trials during investigations. Digital tools are specifically mentioned as being helpful when feasible. Students represent data in tables and graphical displays, again looking at patterns in the data to reveal relationships. They analyze data to make sense of phenomena using logical reasoning, with an increasing focus on mathematics and computation. This includes comparing and contrasting data to look for similarities or differences in their findings. And again, at the bottom of the 3-5 column, we see engineering applications of analysis. Students will be refining problem statements and designs, as well as using data to evaluate and refine design solutions. In 6-8, we see more quantitative analysis, and students are working on distinguishing between causation and correlation. Students use statistical techniques to evaluate data and do error analysis. The elements of this practice in 6-8 show a continuing emphasis on constructing, analyzing, and interpreting data and using larger data sets to identify relationships. Students are distinguishing between causal and correlational relationships and using data as well as evidence for phenomena. More attention is given to the limitations of data analysis and thinking about ways to improve precision and accuracy. Students analyze data to look for optimal operational ranges in evaluating design solutions. And then by 9-12, more detailed statistical analysis is involved. Data sets are compared for consistency, and the use of models helps them generate and analyze data. Students use tools, technologies, and/or models to analyze data to make valid scientific claims or determine optimal design solutions. They apply concepts of statistics and probability to science and engineering questions and problems. They continue to look at limitations of data analysis at a more complex level, and they compare and contrast different types of data sets, examining consistency of measurements. In 912, students evaluate the impact of new data on a model or explanation, and they analyze data to identify design features and optimize the solution relative to success criteria. I noticed that across the grade bands, students are looking at information and identifying patterns. They're using increasingly complex statistical analysis to evaluate data to answer questions. The skills really build on the previous grade band. I think a look at the vertical progression of this practice really emphasizes the importance of science education in earlier grade bands and how that supports more complex analysis of data in later grades. This progression can also help me see if I'm using grade band appropriate techniques of analysis. And if I don't feel that my students are ready for that, I can look at the previous grade band to see what missing skills I may need to address. So let's take a moment and reflect. How can this progression of the practice be helpful in planning? And how could it help inform what you're doing in the classroom with instruction and assessment? Please pause for a moment and share your ideas on how you can use this matrix with your group. In our work with teachers around our state, we find a lot of teachers see this as a useful document to help them determine and define exactly what the practice of analyzing data includes, and to help them plan for experiences within lessons that will build student abilities. It can be used to reflect on a lesson as well and think, was what I did building towards grade band appropriate use of the practice? It can also help define performance tasks that you might want to do with students. Well, as a teacher, I'm always looking for examples of lessons that embed this kind of student thinking and use of the practices. And so that's where we're heading next. We'll explore looking at how we can incrementally increase student use of the practices and see how that plays out in some classroom vignettes. In this section, we'll be using more resources from the NSF-funded project on instructional leadership in the science practices from their website. I'd encourage you after the video to really check out some of the different examples that you can find here. There are video examples, lesson transcripts, and lesson adaptations available to help you visualize how to make the practices really come to life for your students. After Kate McNeil and her colleagues grouped the science practices in the diagram that we reviewed earlier, they started looking at how each practice could be broken down into levels of sophistication as a way to guide and evaluate student and teacher use of the practice on a continuum of complexity. This continuum shows 4 levels, with level 1 meaning that the practice is not observed or not in use, even at its most basic level in a lesson, and level 4 showing a sophisticated use of the practice. While Appendix F provides significantly more detail for each element of the practice at particular grade bands, this continuum shows how students can engage in the use of the practice in developmentally appropriate ways at any of these levels. So here's the continuum for analyzing and interpreting data. The continuum document is in your resources below. This continuum is a reflective tool developed for teachers of grades K-8 to help them take the essence of the practice and scaffold how the practice develops incrementally. You'll notice a pattern. Things we discussed as essential parts of this practice, like grouping and organizing data to find patterns and relationships, are what you see included in this continuum. As we noted earlier, developing student abilities and the use of a practice is a process that happens over time and with multiple experiences. So this continuum can be applied in the K2, 3-5, or 6-8 grade band. Please take a few minutes now to pause the video and look at the continuum on the screen or on your own copy. Notice the differences you see in the increasing complexity of this practice. What are the key differences that you see between levels? You might consider highlighting those things that ramp up the sophistication of the practice, and then restart the video when you've found those key levers and you're ready to go through it together. Well, we see at level 1, students may record some data, but they're not analyzing the data to make meaning or find patterns. At level 2, the teacher is providing opportunities for students to work with data and either organize or group the data. However, they do not look for patterns or relationships within the data yet. At level 3, there's an opportunity to either organize or group data, and students are supported in recognizing patterns and relationships in the information. At level 4, the teacher provides opportunities for students to make decisions about how to analyze and display data, and then they get to work with the data to create the representation. Again, they look for patterns or relationships in the data. So basically in level 2, they do more than just collect data, they're organizing or grouping data. Level 3, they're also adding sense making, looking for patterns and relationships. And in level 4, student decision making is the key lever. Students collect, organize, and group data, look for patterns and relationships, and they make some decisions about how to analyze data. Do you see the incremental progression here? So this is a process, one that's developed over time with intentionality. And now for my favorite part, seeing how beefing up the use of the practices can be done in a lesson. We're going to look at a sample lesson played out at 4 levels of complexity in vignettes that are labeled A, B, C, and D. In your resources, please find lesson adaptation, the lesson adaptation for analyzing and interpreting data. In this lesson adaptation series, Ms. Davis's 3rd grade class is learning about weather patterns over each season. She has her class work with temperature and precipitation data for the past year in their area. The students are organizing their data then into a table or graph, and that same scenario will be played out in 4 different ways. Here's the performance expectation that this lesson is addressing. 3ESS2-1, represent data in tables and graphical displays to describe typical weather conditions expected during a particular season. So here's the task. Please read through the versions of this lesson, A, B, C, and D. Looking at the continuum for data, match the vignettes to the description of the practice. So in one vignette, the teacher will ask the students to collect data, but they don't analyze it. That lesson will be your level 1 lesson, and so forth. So look for evidence in the vignettes that will help you support your ranking 1 through 4. Pause the video now while you read through the 4 lesson versions and rank the lesson adaptations. Some thought questions are on this slide to help you discuss with your group. If you're working as a team, you may want to take a look at those and then restart the video when you're ready to go through the vignette order with me. This could be a longer working break or a PLC. So we're looking to figure out where did you place each lesson on the continuum? What evidence did you find to match those key levers? And then you're thinking about your own classroom instruction. What might be your next steps in bumping up complexity in student use of this practice? Let's talk through these together now. The vignette that scores a level 1 is lesson adaptation C. I have to admit, when you first looked at that lesson plan, it was pretty obvious that students were using technology and looking at data. It was colorful, but that's about the extent of it. They record data from the National Weather Service database, but they aren't really organizing or analyzing it themselves. They're just filling in blanks on a worksheet. Mrs. Davis has students report the data that they recorded, but then she organizes it in a table on the board, and there's no real discussion of what that data means or how it's going to help them answer their question. The lesson that matches level 2 is lesson adaptation B. Students were given data, and their task was to organize the weather data into the table and graph that they were given. Students were given step-by-step directions on how to graph, and they weren't asked to look for patterns or relationships. They didn't make any decisions about how to analyze the data themselves because the table and the graph were already set up for them. Okay, the level 3 lesson is vignette D. Students were given data and given a table and graph to organize the data. After they'd done that, Ms. Davis asked them to use the data to make sense of what the weather is like during each season. She asked them to summarize seasonal patterns, and she provided sentence scaffolds to help them do that. In discussion, students were able to do some analysis of the data and share which season had the most precipitation and apply temperature data and changes to the seasons. In vignette A, we see the most sophisticated use of the practice by students because their teachers set up the experience to allow them to make decisions about how to analyze the data and how to create their own representation. They looked for patterns and relationships in the data as well. So let's think for a minute about what we see here in the way these lessons were presented. Did it take any more money or any more supplies for Ms. Davis to support students in a level 3 or a level 4 use of this practice? It did not. I really like the way that you can see how even young students can analyze and interpret data at high levels of complexity. Undoubtedly, this was not their first experience analyzing data as third graders. However, one thing that we really like about the continuum is that it helps you see how you can make small incremental changes in the use of the practice. You can start by giving students the opportunity to organize and group the data, and then ask them to help look for patterns and relationships in the information. After some guided experiences discussing what kind of data representation is best for different types of information, students will be ready to apply that and make decisions about which direction they want to move. On the Instructional Leadership in Science Practices website, you can find a lesson adaptation series for each of the 8 practices. These practical examples can really help you visualize the continuum and look at your own next steps for your class. So now we're ready to take a look at some strategies that can be used to help students develop their own abilities to analyze and interpret data. Just like there's a lesson adaptation series for each practice, the ILSP website also has a list of instructional strategies for each practice. Once you're on the website, if you click the Tools tab, then select Tools for Instruction. You'll find downloadable lists of strategies. And the downloadable list of strategies for data is also in the resources for this video. The instructional strategies list provides examples of strategies you can use to support the science practice. These strategies can be embedded in lesson plans to help students build their abilities. And these lists are just a start, but we've found them to be really helpful in stimulating discussion of different techniques. So please take this opportunity to pause the video and read through these strategies, discussing possible applications with your teammates. Be sure to add your own ideas to the list. Another strategy we'd like to share comes from BSCS Science Learning. This is called the I-squared strategy, identify and interpret. This strategy is in your resources, and we'll talk through it on the next few slides. If you find that your students are having difficulty making sense out of a set of data, many teachers I know have found this to be a real game changer and a great way to get students more adept at figuring out what data means. Please locate this resource and take just a minute to read through this. Take a look specifically at step 1. So we'll pause here for a moment. Step 1 of this strategy is to identify tangible things in the data set, something that you can put your finger on, physically point to. For example, students may identify trends, dips, differences, and patterns that they see. So then you direct students to draw an arrow to that bit of data and write "what I see" statements. These statements should be simple observations. You are not interpreting them yet. You're just noticing things that you see on the data chart or graph. So students might look at this line graph and they might note that they see an upward slope in the first half of the line between February and July. They might note that they see a peak atop of the line up there in July, and then a downward slope between July and December. So they could write 3 separate I see statements to go with that. Students can write these observations right onto the graph or on a Post-it note that's added to the graph with an arrow directly pointing to the observation. The second step is to interpret what those data points mean. This comes after the I see statements have already been made. You don't want to try to interpret the whole figure at this point, just those noted locations. So take a few minutes now and read how the "it means" statements in step 2 interpret the features you identified earlier. So the upward slope we saw in the first part of the line graph means that temperature is increasing between February and July. The peak we noted in July means that the hottest average temperature in the city happens in July, and the downward slope we saw means the average temperature decreases between July and December. So each I see statement has gotten an interpretation. In step 3, you put the observations and interpretations into a caption that describes the overall picture that the data is telling. You start with a topic sentence about the figure or graph, and then join the I see and it means statements together to build a coherent paragraph. This activity can be modeled and done with a whole group. Students can learn to do this process in small groups, and then eventually it will help them be able to analyze and interpret data independently. So today we worked on developing a deeper understanding of the science and engineering practice, analyzing and interpreting data using a variety of resources. We looked at the NSTA version of Appendix F to see the elements of the practice and how the practice progressed across grade bands. we use the instructional leadership in the science practices continuum to look at strategic ways to increase students' abilities with the key parts of this practice. And then finally, we looked at instructional strategies you can apply in your classroom. Thank you so much for watching. As we close, please take a minute to reflect. What are your personal strengths in approaching this practice? And what are your challenges? What opportunities can you find in your current classroom instruction to incrementally increase student abilities with this practice? And which of the resources shared will you use to accomplish these goals? Again, thank you for your time and commitment to learning more about analyzing and interpreting data and providing students the opportunity to use this practice in figuring things out. Check out the other videos that we have available on the science and engineering practices on our website.